Okay, the timing on this talk is perfect because we've set up a lot of the points that are important now for what I'm going to talk about. So I'm going to discuss some of the human clinical studies and, in fact, really focus on the FEV1 and the dose response between ozone and FEV1 responses, particularly because this is a major basis for the number that the standard is being set at, the level that it's being set at, and how we put it in the context of known actual exposures and known doses.
It's a different slide than this up there.
I got one.
Just a second.
We're okay.
Okay, we.
Oh,
have a
okay,
long
so
slide two.
presentation.
That's
No,
slide two.
that's right.
So that's right, this is page 2, sorry.
Just a second, guys.
We're good.
So there were two presentations that were on your chairs.
Right.
Okay.
Got it.
You got 'em?
No, it's just
Okay.
you started with slide 2 instead of the first one, so I was confused.
Oh,
I'm easily confused, so.
Yeah, same here. Good, we're good.
okay. So this slide, which is slide 2, shows some of the exposure chambers or the exposure setups that people have used for these types of human clinical studies. Typically, they've been done in chambers with controlled atmospheres. In this case, either filtered air or filtered air mixed with known concentrations of ozone. They have also been done with various face mask systems, which is the picture that you see on the left, or sometimes just with through the nose or through the mouth to determine differences in how it's inhaled. Many physiological effects have been measured using these types of experiments. The one that's focused on most and that we've talked about the most today is the FEV1 response. And again, what I'm going to talk about primarily right now, and we haven't focused on quite so much, is the dose, which, as I mentioned before, is concentration, duration, and ventilation. Ventilation rate being really the exercise that we've been talking about. So as it turns out, I actually have the 3 of the definitions that for adverse effects for FEV1 that we've been talking about up until this point. So if you want to refer back to it, they're right here, and the references for those are at the end of this presentation if you want to look them up. So as Dr. Utell mentioned, there is the ATS, reversible loss of lung function combined with symptoms. There is another ATS, European Respiratory Society definition, which is a 2-point short-term change, which would be the type of change you would see in these types of clinical experiments of greater than 12% or greater than 0.2 liters, may be clinically important. And then the bottom is the EPA's numbers that they've been using, where they consider a 10 to 20% change to be moderate, the lower end of that to be of interest for sensitive people, for potentially sensitive populations, particularly those with lung diseases such as asthma, whereas perhaps a 15% decrement is more relevant to healthy adults. So that's there for your reference. This curve, these curves were plotted by McDonnell in 2012, and I'm showing this because it's the basis for the risk assessment dose response that EPA uses. I'm not going to spend very much time on it, but I wanted to point out that a couple of things. One is that I call this a dose response, but you'll see at the bottom, the x-axis is concentration. It's not dose. So this assumes, these concentrations assume that a person is exercising at 20 liters per minute per meter squared of body surface area, which is approximately 34 to 40 liters per minute, if you assume certain body surface areas, for a duration of 6.6 hours, where they're exercising at that high, that 20 liters per minute per meter squared, for 50 minutes out of every hour for 6 hours over a 6.6 hour exposure. And they have they show a clear sigmoidal dose response. You can see the very top line is their mean dose response. The 3 lines below it, the 3 curves below it, refer only to that proportion of individuals who have a greater than average response. So they see a greater than 10% FEV1 decrement, or greater than 15%, or greater than 20%. And this is the type of output that we see with the EPA risk modeling. So I just wanted to point out that this is where it came from. I want to show you briefly some work that we've done, and it's worked out well because these are kind of the graphs that show a lot of the data that have been spoken about today. So what you can see here is 2 dose response curves. These are people that have been exposed for either 6 to 8 hours on the left, or for less than 3 hours on the right, to various doses of ozone. So the x-axis here is dose, which is that combination of duration, ventilation, and concentration, which is why it's in a different form, which is parts per million liters. So you can see the variability in response. This is a great way to see all of these data points are individuals who have been exposed. And what is really of note and helps us to kind of understand what the variability can be just from doing these experiments is if you look at those points that are on the 0 line. So I plotted the filtered air responses, and you see quite a variability of response in terms of just exposure to filtered air. So some of them, as Dr. Dourson has pointed out, have an increased FEV1 after response or after exposure to filtered air. Some of them have a decrease down to 10, 15% FEV1 decrements just from that experimental controlled exposure and not anything to do with ozone. So it kind of gives you a feeling for what the variability of responses can be. And then with increasing dose, we see an increasing response that's also similar to McDonald, can be expressed with a sigmoidal relationship. These are the two dose response curves. The blue curve is the long exposure, 6 to 8 hours. The red curve is the shorter exposure, which is less than 3 hours. And these are two statistically significantly different curves. So actually similar to what Dr. Utell was saying, the shorter exposures cause a more severe effect. And what we can say then is that at a similar dose, the longer it takes to get to that dose, the lesser the response that you see. And this is consistent with a mechanism of replenishment of antioxidants over time with exposure to ozone. And in fact, they may be upregulated. We don't know that for sure. Now, it's, as we've talked about with sensitive populations, these experiments have actually been done with sensitive populations, as we've discussed, both long exposures and short exposures. The diagram I'm showing you here is with short exposures. Probably doesn't surprise anybody that more of these types of experiments have been done with short exposures with sensitive populations than with long exposures, but the conclusions come to the same thing. The red points are the group mean responses of young, healthy adults, typically 21 to 35, in that range. All of the gray shapes would be considered at risk or populations of concern. The circles are children. There have been some studies with children. These are 8 to 11-year-old boys, and they show a similar response, so they can fit the same dose response curve. The gray squares are asthmatic adults, and they also fit a similar dose response curve. The triangles are adolescents, so these are between the ages of 11 and 16. It's a bit more difficult to interpret with that group because the doses were very low for these experiments, very short experiments, and they don't actually show a dose response curve within those exposures. The most severe FEV1 decrements were to filtered air. But this is both asthmatic and healthy adolescents, and they show relatively comparable responses to ozone. So this allows us, if we're using this dose response curve, we can show that we have this dose response curve also captures those other populations that have been tested. That is true that these are mild asthmatics, but these are the ones that can actually do the experimental protocols. From this, we've taken some threshold doses of ozone, which means that we looked at the dose at which you would see a group mean, for example, 10% FEV1 decrement for a shorter exposure or for a long exposure, and also for some other FEV1 decrements. And these are those dose thresholds from 0 to 20% FEV1 changes. For the long exposure, there is no dose threshold for a 15% FEV1 decrement because the responses never go that low for the mean responses. And similarly, there is no dose threshold for the 20% FEV1 changes because the dose response curve never gets down to 20%. The sigmoidal evens out before that. Now it's nice to know that we have these dose thresholds that we can derive these dose thresholds for these group mean responses, but they are in the form of parts per million liters, which isn't so helpful if we're trying to decide on levels and averaging time and that sort of thing. So it kind of has to be translated back where you pull out concentration and duration and time so that we can really interpret it in the context of what somebody would actually be expected to be exposed to. So for ventilation rates and durations, there are actually diary data where we know what actual people, what kind of ventilation rates they're exercising at and what kind of durations. So this is focused on exercise because, as we've discussed before, you really need exercise to bring the ventilation rate up enough to have a response, particularly at ambient ozone concentrations. Although I say they're exercise, there are some sedentary numbers here. So we know what the ventilation rate, for example, for somebody who is just, well, for us, we're just sitting here. And these numbers are derived from a number of sources. There are a number of EPA sources where they've looked at the diary data, and they say that these are the average and then the various percentile ventilation rates, and these are the durations for which those groups were exercising at that ventilation rate. And for different age groups, for different genders, although here I have combined the genders. There are also ventilation rates about 2/3 of the way down that chart that are used for risk assessment purposes. So these are the US EPA 1994 numbers, the non-occupational, which is a 24-hour ventilation rate, which is 20 meter cubed per day, or 14 liters per minute, and an occupational manual labor ventilation number, which is 10 meters cubed for 8 hours, or 22 liters per minute. And there have also been studies that look at various populations to see what their ventilation rates are and how long they keep those ventilation rates, which is the Zerbier and the Samet at the bottom. So we can use those as surrogates for what actual exposure ventilations and durations could be in the population. So the other piece of this is the ozone concentration. And I was pleased to have included this next slide because it comes to Roger's point about the importance of the averaging time when we consider ozone concentrations. So we think about 75 parts per billion and 70 and 65 parts per billion, but it is very important to point out that that only applies to an 8-hour averaging time. So what you're seeing on this slide is the 16 one-hour measurements. These were taken at a monitor in Dallas-Fort Worth in 2014. And if you just look at a 1-hour maximum number, which is one of our older standards, is a 1-hour maximum, you can pick out of that list what that day's 1-hour maximum, and that's 87.5 parts per billion. That same day, we can calculate an 8-hour maximum average. An 8-hour maximum average is when you take eight consecutive hours of that day and you calculate the average. Then you move down 1 hour and you calculate the next average, and so on as a rolling 8-hour average, and then you pick the highest one. So for this particular day, 74.6 was the highest 8-hour maximum average. So this is a day that just meets a 75 part per billion standard. We can do this for any other combination of averaging time. So you can do it for a 4-hour maximum, and that number is 80. You can do it for a 12-hour maximum, and that number is 67. And you can calculate a 24-hour average if you just average all 24 measurements for that day, and that number is 49. So depending on how long you're exposed depends on what the concentration will be, even if you meet a 75 part per billion 8-hour average number. So if somebody's exposed for 4 hours, we don't use a 75 number. We use an 80 number, or whatever the appropriate number is. It would be 80 for this day. And there's variability in that. The other thing, because Roger brought it up, that I want to point out is the form. So the form of this standard, just to repeat for anybody who's not aware, this is the 75 part per billion 8-hour maximum average, the fourth highest in a year averaged over 3 years. So if we just look at 1 year, that means that we can have 3 days of that year that are over 75 parts per billion. We can have 1 day that is at 75 parts per billion if it just meets the standard, and then the other 361 have to be below a 75 part per billion maximum average. So it's important to keep this in mind when we think about what the exposure could be to the population. The other thing to keep in mind is that these are maximum averages, so if somebody is outside for 4 hours on this particular day, they could be exposed anywhere between 37 and 80 parts per billion. So it depends on which 4 hours. So it's the complexity of the problem in terms of understanding the exposures. But I just wanted to put that into the context of what these concentrations really mean when we're monitoring and what we're talking about. What I did was I took so we can start looking at the concentrations. If you had a 75, a 70, or a 65 part per billion day. In Texas in 2014, I took 10 days where the 8-hour maximum average was either 75, 70, or 65. And I looked at what the maximum average was for these different averaging times. So we could say, if I have a person who is exercising for 4 hours, what would I expect their ozone concentration exposure to be? And so that's what this table is that you're looking at here. And I pointed out the 8-hour maximum average, which is 75, 70, or 65. And this is just a small sampling. This was just 10 days that I picked from Texas to get an idea about what these other numbers could mean on those 8-hour maximum averages days. But what that means is that we can combine these things all together, which is the next slide. And we can do an ozone dose calculation, which allows us to compare it back to the thresholds. So for example, if we had a child who was exercising at moderate intensity, we can pull that out of those EPA charts that I showed you a couple of slides ago. And that ventilation rate is on average 21.6 liters per minute. The time that they spend at that exercise ventilation is on average 2.6 hours. So that's an approximately 3-hour exposure. So we'll pick a 3-hour maximum ozone concentration to calculate that dose. And those 3-hour maximum ozone concentrations at a 75 part per billion day, a 70, or a 65 are shown there. And then we can do the dose calculation. It's very simple. You just multiply them all together and converting the part per billion to part per million, and we get this range of doses depending on the ozone concentration of somewhere between 237 and 279 parts per million liters. And then that can be compared to the threshold. So the thresholds being at the bottom. This is a less than 4-hour exposure, so we would use the short exposure curves. I did this for a number of the different exercise scenarios that I showed you. And this is the short exposure scenarios, anything less than 4 hours, so I'm comparing it to those dose thresholds. And there are a couple of things here. I'm showing the dose thresholds for 5%, 10%, and 15% FEV1, and these are all well below the 5% FEV1. The other thing I want to point out is that we have 3 different lines here, one for the 75 part per billion day, one for the 70 part per billion day, and one for the 65 part per billion day. The doses are very similar between those 3 days because the concentrations are very similar between those 3 days. Similarly, for the long exposure scenarios, most of these are below the 5% FEV1 threshold line, including the very last one, which is the 8-hour manual labor ventilation rate and duration, 8 hours obviously. The only one that starts to touch even the 5% FEV1 mean decrement line is the 24-hour exposure. And this one is worth noting a couple things about. This is a 24-hour ventilation. It includes 8 hours at the higher manual labor ventilations. Because ozone, as we've discussed, is an outdoor air pollutant, it also assumes that a person is outdoors for the entirety of those 24 hours. And the last point I want to make about this is that I mentioned at the beginning that the longer the exposure, the longer the time it takes you to get to the dose, the lesser the response seems to be. That's what the data shows. This is a 24-hour exposure, and we're comparing it to a 6 to 8 hour dose threshold. So really, a 6 to 8 hour threshold is going to overestimate the effect that you would see from a 24-hour exposure. And with that, I'm going to give it back to Dr. Dourson.
Okay, Dr. Lange, thank you very much. So at this point, let's open for clarifying questions. And I believe after the questions, we're going to need a break. Does that sound reasonable? Probably. So, gentlemen, clarifying questions to the presentation, perhaps?
I'm hoping that the folks in the audience can do those calculations and get back to us and do the presentation. This is very complicated.
It is really
It is really, you deserve, it's really neat, and trying to understand not only how you did it, but the impact it could have, because it really says there's a big difference between the short-term exposure in terms of the decrement and the longer exposure, and the 8 hour. This has lots of implications for the 8 hour effect. And I guess my question, have you written this up?
It's actually one of the documents that we
No, I mean published.
We're in the process of doing that.
It's really, it's fascinating. It's really neat stuff.
Okay, other clarifying questions or comments? I had a clarifying question on slide 4, please.
Slide 4, yes.
That's the McDonald 2012.
Mhm.
Okay, so here's the question. You said the EPA is using this. And, yeah, that's the next one. Yeah, there it is. So I think the first question is the y-axis on the right side applies only to the 3 lines below. It doesn't apply to the median response, right?
That's correct, yeah.
Okay, that median response runs into 0.8 and it shouldn't run into anything.
Right.
Okay, that was helpful. But here's the real question. So I work with US EPA and a number of 8 groups with reference concentration, the other air toxics, you know, the couple hundred of those or whatever they are. And you quoted the EPA's, US EPA 1994 subsequently in one of your tables. That's the US EPA's reference concentration guidelines,
Mhm.
where the ventilation rate is 20 meters cubed per day or 14 liters per minute.
Yes.
So we have, here's the question. So am I to understand that for air toxics, US EPA is using 14 liters per minute for 187 chemicals or whatever they've got for air toxics? And for the NACS pollutants, they're using a ventilation rate of 34 to 40 liters per minute?
That's what these experiments have been done at, yeah. And that's what this graph is being done at, because most of the experiments were done at that ventilation rate.
All right, so somehow if total dose was relevant, which you're saying it is, if it's all the same duration, then what that would do is it would if we were to use EPA's 14 liters per minute, it would displace all those lower curves off to the right. Is that correct?
Yes, yeah, because your total dose would be different.
And it's almost like it's a the difference between 14 and whatever numbers you gave is about 2 to 3-fold.
Yeah,
So it's a 2 to 3-fold shift to the right.
yeah. Although 14 liters per minute is for a 24-hour exposure. So you could use a manual, so there's an occupational number, which is it's a 10 meters cubed per 8 hours, which is
Right.
22 liters per minute, although that's still considerably lower than the 34 to 40 liters per minute that was used to generate these curves.
Thank you. Other clarifying questions? We have a clarifying question, yes. Dr. Portney?
Sabine, would you look at, or bring up slide 13? I think that there's a typo on that, but let me see.
That's the 03 dose calculation slide?
No, it's
No, I think it's the.
next page. So under
Yeah.
the heading dose calculation, it looks to me like you're multiplying the same things on those 3 lines and getting different numbers. Don't you mean for 70
Yes,
parts per
yes,
billion?
you're right. Yeah,
Okay.
you're absolutely right. Yeah,
Okay.
yeah.
Okay,
Yes, yeah, I
so where's the
apologize. Thank you.
typo?
Could you?
So it's
oh,
the,
It should be 75.3.
it should be 75.3 and 70.3. Yes, thank you very much. That's completely correct.
No, I'm
Where?
sorry, I've still lost it.
So
Yes.
under the dose calculation, there are 3 lines. There's 75 parts per billion,
Yes.
21.6 liters per minute times 156 minutes times 0.0828 parts per million.
I'm on it.
And then the 2 lines below it are also 0.0828 parts per million, and those should be the different concentrations.
Okay, so we'll make sure that gets corrected during the break,
Yeah.
right? So that our,
Yeah, the answers are still correct. Yeah, it was just, it
Oh,
was
that's
a, it
always
was a
good.
copy and paste thing.